Last time we were discussing about the integral forms of the conservation equations, and as an example we looked into the integral form of the mass conservation and its corresponding differential form also we revisited, and we found out that it is possible to convert one form to the other. Now let us look into some more examples of the use of the integral form of the mass conservation equation. Let us say that you have a wedge shaped element like this with the axis oriented along x and y, and the velocity field is a 2-dimensional velocity field is given by, say, u is given by this, v is given by this one, and 2-dimensional w is 0. Let us give some names to the faces of the elements here. The objective is to find out that what is the volume flow rate through AC. The dimensions are given, let us say this is 1 meter or just 1 unit, all are given in some consistent units, say this is 2, these are given. Okay. So what we also are assuming that V0 is a constant, it is not a function of any other variable that we are looking for. So how should we proceed with this problem? Let us say that we are interested to use the integral form of the mass conservation, and that is one of the natural things that we should use here, because there are the 3 phases across which fluid will enter and leave. So the net rate of transport should be given by the integral form of the mass conservation, that is you have dm dt for the system plus this for the control volume plus integral of rho the left hand side is 0, because no matter whatever system you are considering, it is by definition of fixed mass. The right hand side, because we are assuming that rho is not changing with time, neither the control volume is changing with time. So what is our control volume? Let us say that this triangular shaped element is our control volume. So whenever we are making a control volume analysis, it is important to identify what is the control volume that we are taking, because you may take different control volumes. Of course for this problem this is an obvious choice of the control volume, but there could be problems where there could be many different choices of the control volume. So the equations that you are writing should be pertinent to a particular control volume that you have chosen, and that should be clearly mentioned. So this triangular shaped thing is a fixed control volume, the volume of that is not changing with time. So it is not a deformable control volume, neither the density is changing with time. So this term goes to 0. So what remains is this net term, which is nothing but basically the net rate of outflow minus inflow of mass equal to 0. So if rho is a constant, let us make a further simplification that rho is a constant, then this will boil down to basically integral of v dot n dA over the control surface equal to 0. and when we say V, here the relative velocity and absolute velocity are the same because it is a stationary control volume, it is not a moving control volume. So this, now we may break it up into 3 parts because the control volume has 3 different distinct oriented surfaces. So you can write this as the sum of the effects of AB, BC and AC. So for AB, when you write, what should be this corresponding expression? So let us identify that, where is that AB. So you are looking for this face, you are interested to find out what is V dot n, integral of that over the entire area. So one important thing is, here n is not a variable, it is like a line oriented along y axis. So n is a constant. So for AB, what is n? So let us try to identify the what are the normal directions for the different edges. Here the edges are all straight lines, so they have unique normal directions. So let us say AB, what is the n for that? Minus I. Then BC, and AC. So for AC, let us say that this is the unit vector normal. So this will have its components. Let us say this angle is theta. So if the angle between the normal and the horizontal is theta, then the angle between the edge and the vertical is also theta, right. That means you can say that n is definitely cos theta I plus sin theta j, where you have tan theta equal to 1 by 2. Okay. So what will this imply? This implies that like you have identified the direction normals for all the faces, only thing you require is the velocity. So the velocities for the faces, for AB what is V? Let us write the, in the same table let us try to write what is the velocity V cap. So for AB what is V cap? For AB x is 0, so u is not there, there is some V, okay. So it is minus V0 y by L j. For BC similarly you have y equal to 0, so it is V0 x by L I, and for AC it is the real the sum of the two components, because here x and y are both non-zero. So we are not writing it because it is like, let us just write it as in general ui plus vj. Now to get the integral, you have to keep in mind that if the velocity varies along that length, then you have to integrate it over the length to get the total flow rate. When you come to the, so let us start with AB. You can of course evaluate this, try to evaluate this, but let us not do that bulwark. You see that the velocity along AB is like it is oriented along AB, so there is no normal component of that. So there is no net flux or influx or outflux of flow across AB because there is no normal component. So if you make a dot product of this, that you can clearly make out, and so that will not give rise to any net flow. Same might be true for BC, right. So the choice of the axis here has been such that if this is the velocity field, then that is the case, but the same is not the case for AC, right. So for AC, how will you find out what is the total or the net rate of flow? Yes. So if something there is nothing that enters here, there is nothing that enters or leaves here, you expect that there is nothing enters or leaves here, right. How could you verify? By doing the integral that it should be 0? No, that is what, like this is QAB, this is QBC, this is QAC, like if you evaluate by doing the dot products, will the dot product automatically give it? It is expected that the dot product to integral over that should automatically give it. So that you should check, so that it gives you a confidence of how to calculate that, because here I have given a special type of velocity field, so that actually this problem solution is not necessary. I mean, I am trying to go through this through a formal route to give you an idea of what should be done in a case when the problem solution deserves that, but here actually it does not deserve. So this is a more intuitive case where nothing is entering and nothing therefore is expected to leave. Now if by chance you get something which is leaving through this and nothing is entering, so that will really violate the law of mass conservation. So that one has to be careful of. Now let us look into some other problem which is not as trivial as this one. So another example. Let us say there is a tank like this, the velocity profile at the exit of the tank is through this pipe is given by this one, and in terms of a local coordinate system, this let us say that the local coordinate system is x1 y1, it is given as u1 is equal to some u0 into 1 minus y1 by y1 square by h square, where y1 is the transverse coordinate and h is this height, and the fluid entering here, the again in terms of the local coordinates you can specify it, but that specification may not be necessary because it is given that it is a uniform velocity profile here with a velocity u infinity which is uniform, and let us say this is h by 2. Okay. The directions of the axis are not given, that means it is not given that what is this angle theta, say theta 1, it is not given, that what is this angle, say theta 0, these are not given. What is given? It is given that the density is a constant. You have to find out what is u naught. Given the width of this figure perpendicular to the plane where it is drawn is uniform. Okay. So, u infinity is given, h is given, these two things are given. Okay. So, how will you go about it? Again looks like a situation where mass conservation should be applied, and if you want to apply the integral form of the mass conservation, let us say that we consider a control volume. So, what should be a good choice of the control volume? So, a good choice of the control volume is something where across the surface we are totally confident about the velocity field. So, let us say that we make a choice of the control volume something like this. So, with this choice of the control volume, you can write the law of mass conservation. If you want to write that, then like it is, because rho is a constant, again it will boil down to a case very similar to the previous one, where eventually it will be integral of v dot n dA over the control surface equal to 0. The remaining terms will not be relevant. So, this is the only term that is relevant. Now, out of the surfaces that you have, only you have one inflow and one outflow surface. Across the other surfaces fluid is not flowing. So, those surfaces are not relevant. So, you may break it up into two integrals, one for this inflow and another for the outflow. Okay. So, the first one is very straightforward, let us do that. So, when you have the v dot n dA, see this v is uniform over the area over which it is flowing for the inflow. So, you can take away this v out of the integral, not only that, the dot product also, because n is also a constant here. So, v dot n entire thing you can take out of the integral. So, what it will become? It will become v dot n into area of the face over which it is coming. So, let us call that this area of the face is here A naught, and here the area of the face is say A1. So, when you write v dot n, you have to keep in mind that what is the direction of n in along this surface. So, the direction of n is opposite to v, right. So, v dot n will give the minus of the magnitude of v. So, for the area 0 or area O, it will become, this term will become what? Minus u infinity into h by 2 into the width. Let us say b is the width perpendicular to the plane of the figure. Then the other area for A1 we cannot have the same consideration because the velocity varies over A1. So, to see how the velocity varies with A1, we are along A1 we are already given that with respect to the local transverse coordinate how it varies. but n is a, but you have to keep in mind that forget about that functional dependence on y1, u1 is going out of the area, and what is n? N is also oriented out of the area. This means that if you just take the vector sense v dot n, that will give you the magnitude of v into 1, because the dot products are in the same dot products of two vectors in the same sense, that will be leading to that conclusion. But because it is varying with y1, now you have to really do the integration. So when you first have v dot n, that will become u0 into 1 minus y1 square by h square, that will be v dot n, and dA is what? Say you take a small element on the axis y1. So this is a small element of the area. So what is that small element of the area? Say at a height y1 from the center line, see the coordinate system is from the center line. So at a height y1 from the center line, say you have taken a small area of width dy1. So the elemental area, which is like the dA given symbolically, it is dy1 into b. If you integrate that from minus h by 2 to h by 2, then that will represent that what happens for the area 1. So sum of these two should be equal to 0. Clearly from the minus sign of the first term you can make that it is inflow, and the plus sign of the second term means that it is outflow, and it is possible to complete this integration in a very simple way. We are not going into that, just to save some time, but important thing is that, see, this is the variation of u over the section. So you can write it equivalently as integral of u dA in the fundamental form in a scalar form. So this is not like a vector form, so it is like just like, because eventually with the dot product it has become a scalar. You have to keep in mind this u is nothing but the component of velocity which is normal to the area. Here fortunately all component is normal to the area, there is no component which is cross that. So this you may express through some quantity which is called as average velocity. So average velocity is this divided by the area. That means if this velocity was uniform but the same flow rate was there, see, if it was uniform, then that uniform velocity times the area will give you the flow rate, that is what the first term has told us. And if it is not uniform, obviously you have to integrate it to get the flow. So if the flow rate were uniform in a hypothetical case, sorry, if the velocity profile was uniform in a hypothetical case, but the flow rate becoming still the same as it is in the real case, then if you equate those two flow rates, then that equivalent hypothetical uniform velocity, this is called as average velocity. So it is like a equivalent uniform velocity that would have prevailed across the section, satisfying the same volume flow rate as it is there in the real case. So therefore this is like as good as some u1 average into a1, and this is just like u naught into a naught. So it is just like a1 v1 equal to a2 v2. You have to keep in mind again that what is v1 and what is v2, these are very important. Again I am repeating, these are fundamentally the average velocities over the sections 1 and 2. See, when we are writing here 1 and 2 or maybe 0 and 1 or whatever subscripts, there is a fundamental difference from what we wrote for using the Bernoulli's equation. Those we wrote for points 1 and 2. Now we are writing for sections 1 and 2. So maybe subscript wise they look very similar, but meaning is entirely different. When it is uniform, it does not matter, it is as good as writing for a point, because velocity does not vary from one point to the other, but you do not have anything called as area at a point. So it is basically when you write A1, no matter in the context of what we write what we have written earlier for 2 points, when we use the Bernoulli's equation, we should keep in mind that there also A1 was for the section that contained the point 1. So it is not that area of a point 1 or something like that, but there we use velocity at the point 1. The reason is that in the Bernoulli's equation we used velocity at a point. So we had to link it with velocity at a point. Now it is like we are linking things through velocity over an area. So if you complete this problem, you will get what is u naught, because all other things are known. Now let us look into some other examples where maybe we look into different case, maybe unsteady case. Let us say similar problem where you have a tank like this, and there is a free surface here. So in the previous problem we assume that there is no change in level of the surface in the tank, but in reality that does not happen. So that is something which is a bit hypothetical. In reality it may happen that approximately the change in this level is 0, because this is such a large area that no matter whatever is entering and leaving, it is not changing the height, and these types of tanks are called as constant head tanks. So they maintain constant head because with respect to the inflow and outflow the change in height of this is so small, because of maybe this is a large reservoir. So the area is so large that it does not change any level, but the more realistic version of the previous problem is that yes, the level of the water will also change. So let us say that the height of the free surface from the bottom of the tank is h. Just to simplify the situation, we now go back to a case of a uniform velocity profile, because we have already seen that if it is non-uniform, that it is not a very difficult thing, we have to just integrate the velocity profile over the section. So with that understanding, let us say that you have a situation like this. Let us say it is uniform, so you have a velocity v1 here, and let us say area of cross section a1, you have a velocity v2, area of cross section a2. When we were talking about the previous problem, see, we could get rid of the situation of change of height of the tank even in a real case by some approximation that yes, the rate at which the water is entering is the same at which the water is leaving. So it is not changing the height of the level of the tank, but when both are entering, that is not the case. So here the only chance of the height of the tank or the level of the water in the tank not changing with time may be only for the consideration that if the area of cross section of the tank A is so large as compared to the others that the corresponding change in height is very small. Otherwise here there will always be a change in height, smallness or largeness depends on the areas. In the previous problem you could cleverly come up with a situation where there is 0 change in height by making sure that the rate at which it enters is exactly the same at which it leaves. So it appeared to be a bit hypothetical, but it is not that hypothetical if it is really doing that. So if you have a reservoir and water is entering and leaving at the same rate, why should it change the level of the reservoir? It will not, but here both are entering. So here our objective is to find out how the height is changing with time. Given these velocities, areas and the information that these velocities are uniform over the area. Okay. So let us take a control volume again. Write the equation. So dm dt for the system is equal to this one, left hand side 0, right hand side the first term, let us assume that the density is a constant, let us say that is given. Okay. So if the density is a constant, it will come out of the integral. But the volume is not a constant. So the volume within the control volume is what? It is A into H. A is the cross sectional area of the tank and A is the height. So this effectively boils down to what? This effectively boils down to d dt of rho into d dt of AH. Area of cross section is a constant, so this is as good as rho A dH dt. See, H is a function of time only and nothing else, so this partial derivative becomes an ordinary derivative here. And what about this term? Yes. So it has now effect of the two areas 1 and 2. So because we have seen that formally what is the consequence of the dot product and all those things, we will now try to write it directly without going through that route. So for the surface 1 what will be? Minus rho V1 A1, and for the surface 2 minus rho A2 V2, right. So sum of these should be equal to 0. So from here you will get what is dH dt, that is very straightforward. Again you can make an observation that if dH dt equal to 0, that is not a possibility because these two terms of the same sign cannot cancel that, and only way it can cancel if V1 and V2 are of opposite sense, that is if one is entering the other is leaving, and then it again boils down to A1 V1 equal to A2 V2. So that is like a previous case that we had considered. The other important thing that we might discuss in this context is that can we try to choose a different control volume. Let us say that we choose a control volume which is not the previous one, but say the new dotted line that I am drawing. Fundamentally there is nothing wrong, but it will not help us solving the problem. Why? Because now the control volume is cutting across some flow surfaces across which you do not know the velocity profile, or you do not know how the velocity is. So how will you find out this integral term? You have to have those locations where at least you have an idea of how the velocity is varying or what is the velocity. So the choice of the control volume is not that it is only something which is unique and you cannot choose anything else, but if there are many alternatives you have to find out that what are the unknowns and knowns involved with that alternative, and it is wise to choose a control volume which gives a very easy situation by reducing the unknowns, and the initial choice that we made is an obvious choice towards that. Let us take another example of similar type, maybe a bit different. Let us say that you have conical tank, just for a change, of radius capital R and height capital H. There is a small hole at the bottom of the cone through which water is coming out with a velocity V and because of this leaving of the water, the height of the water in this conical tank is reducing. Maybe initially it was the full height capital H, but because water is leaving, at some instant of time, say the height is like h, small h. So this small h is changing with time because water is continuously leaving, and let us say that it is leaving through the small hole with radius of small r. Both like this is a circular hole and cone is of course a circular cross section. Then you have to find out what is dH dt. It is given that you may approximate VE by root 2 g small h. It is given. We have seen earlier that this is not actually a very correct estimation, but it gives a sort of approximate situation under certain simplified assumptions, and we have discussed those assumptions in details when we were discussing about the Bernoulli's equation. So this problem is fundamentally not very much different from the previous ones, except that the geometry is such that you have a variable cross section area, nothing bit I mean more complex than that. So let us try to use the conservation of mass here. So the first term, what it will be, again assume rho is a constant, then if rho is a constant, so the bad thing that we have approached is like this, that we have tried to solve the problem without identifying the control volume. I am trying to just do it in the same way in which you are habituated to do, just like straight away going to an equation and solving a problem. Now see, it is ridiculous. We are trying to apply an equation for a control volume, but we do not know what is the control volume, and that perhaps we were trying to do. So let us identify a control volume. We will identify one type of control volume, and I will leave it on you as an exercise to identify a different type of control volume and come to the same answer at the end, and that will give you a good idea. Let us say that we identify a control volume like this. Let us say with respect to that control volume we are writing this term. So with respect to this control volume, when we are writing the term, you have, let us say that we neglect the density of the air which is there at the top of the water in comparison to that of the water. It is not a very bad engineering assumption, because the reason is that air is much lighter than that of water, right, typically 1 by 1000. So in fact that is what we did also in our previous problems, where if you have a tank, maybe in the tank some part is water but the remaining is air, but when we wrote this term we did not write the term corresponding to air. So that was an inherent assumption that we were making or keeping in mind but not explicitly stating. So then like if you take rho as a constant and out of the integral, what will become this integral of dv, so that this term will become basically rho derivative of v with respect to time. Now the volume is the volume of the water. So at this instant that we are considering, the volume of the free surface is located here. So the volume of the water is 1/3 pi local r square. So let us say, let us give it a name, say r1, 1/3 pi r1 square h, and from the semi vertical angle of the cone, let us say theta, you have tan theta is equal to r1 by h, which is same as capital R by capital H. So it is possible to write the whole volume in terms of small h. So the whole volume becomes 1/3 pi, in place of r1 it is h tan theta, so h cube tan square theta. Then the other term, what will be this one? How many flow boundaries are there in the control volume? Only one flow boundary, only one exit boundary. So what is that? So in this boundary v and the normal vector are located oriented similarly, so the dot product will give a positive term. So it will be rho, then what? So v dot n, v is uniform over the area, let us assume that. So v dot n will come out of the integral, rho will come out of the integral, and integral of dA will become a. So it will become like rho ve into ae, right. So it will become rho into ve into pi r square, okay. So then it is very straightforward, these two together is 0 and you can differentiate v with respect to time. It is like an ordinary derivative again because h is just a function of time. So 1/3 pi into 3h square dh dt into tan square theta. So if you substitute that here, you can find out that what is dh dt. At a given instant when the height is h, small h, okay. Now I will leave on you solution of the same problem but with a control volume choice like this. Say you have a control volume which is adapting itself with the movement of the water. So this control volume is a moving or a deformable control volume in a way that if the water level is coming down, this is also coming down with it, okay. So this type of control volume, and then with respect to that type of control volume you make the same analysis and try to come up with the same answer, okay. Let us work out another problem. Let us say that we have a rigid tank, spherical tank, which contains air. And originally there was a valve located here which was preventing the air inside to go outside. Now the valve is opened, and once the valve is opened, the air will go out of this pipeline which is connected to the tank. It is given that number 1, the state is uniform within the tank, in tank and pipeline. That means the properties are the same at a given instant of time everywhere that we are considering. And number 2 is that the rate of mass flow out is proportional to the density at that instant. Okay. This is given. You have to find out that how the density is changing with time. It is expected that the density will change with time because it is a rigid tank. Because it is a rigid tank, if you take away air from it, its density will fall because now less mass is occupying the same volume. So that you have to find out that how that density is changing with time. Again, let us start with the choice of a control volume on which we want to have our analysis. So the control volume, let us say that we choose a control volume like this. If we choose a control volume like this, it does not matter whether the valve is opened or closed, right, there will always be a flow across it. So now if you are asked that what happens after the valve is open, you should take it like I mean, of course the pipeline does not end here. So the pipeline continues beyond the valve. So you should take it like where the effect will be apparent when the valve is open. But again, in this particular case, and only if our objective is to look for a mass conservation, it makes no difference as such, because even if you take your control volume like the surface which is to the right of the valve and to the left, right, at any instant whatever is the mass flow rate here, the same is the mass flow rate along this pipeline in terms of the mass flow rate, but that may not be the case if the density in the pipeline itself is a function of time. So if the density in the pipeline is a function of time, and if there is a possibility of like see, variable density cases are very typical cases. So for variable density cases, it is not so trivial to say that like the mass flow rate is the same in all cases, but here no matter how the density varies, you can say that these two mass flow rates will be the same. Why? Yes? Area of cross section is same. So density is like I mean whatever it is, like even if you forget about the density, like just fundamentally think, if you have a mass flow rate that goes out of this, if the same mass flow rate does not go out of this, where does that mass go? Is any mass like accumulated in between? No. Velocity may be different if the densities are different, but if the density is uniform, then that may be ruled out provided the time dependence of the density is not creating any big change. So if you see that like what happens within this pipeline in terms of the velocity or density is something we do not have enough information really to talk about that, but one important information we have that whatever happens individually to velocity density, but the mass flow rate what goes through this is same as the mass flow rate that goes out, because where otherwise it will go, it cannot sit on the valve that mass. So we are assuming that there is no accumulation, it is a steady flow system. So if it is a steady flow, like whatever enters here the same leaves here, then it does not matter really whether your control surface goes through this or whatever. Now let us look into the different terms in this expression. So if you look into the first term, so here it is a rigid tank. In the previous class we tried to solve a similar problem which is like a flexible balloon. So there the volume could change with time, that is maybe if it were a flexible balloon, you could have expected that by taking away air out of it the balloon will try to shrink, but here it is a rigid tank, so it cannot respond to that, it can only respond to that change by having a change in density inside, but not its change of its own volume. So the volume of the tank is the density of the fluid in the tank is definitely varying with respect to time, but the volume is not varying with time. So that means you can, the first thing that you can do is you can take the time derivative inside, because the volume of the control volume is not a function of time anymore. And the next thing is that how this density changes with respect to time, that does not change from one point to the other within the control volume. Why? Because it is given that is uniform state in the tank and in the pipeline, that means the density may change with time, but at a given instant of time the density is same everywhere within the control volume. So that means this is like an isolated term which does not depend on the volume. So this you can take out of the integral, so that means eventually it will become the volume of the tank into the rate of change of density with respect to time in the tank. Okay. So it is not so difficult to come up with this expression, but we have to keep in mind that what are the important assumptions that are leading to this type of a simple proposition. If the density was varying within the tank itself, then we could not write it, then we had to integrate it by keeping in mind that rho is a function of both position and time. Here the dependence on position we have frozen, we have assumed that that is not there. Then for the next term, so if you see that this, now you have only one outflow boundary for the control surface, when the valve is opened the air is leaving here, so you have an m dot exit which is the rate of mass flow rate out. So the rate of, see this is eventually giving what, this is giving a rate of mass flow rate, outflow minus inflow, there is no inflow, so only outflow. So this is as good as plus m dot E, this is equal to 0. What is this m dot E? M dot E is proportional to the density. So let us say that m dot E is equal to some k into rho. So this rho is an instantaneous density, that at that time whatever is the density in the system, proportionate to that the mass is coming out. So this you can write some k into rho, where k is a constant. So you can, the next work is very easy, all of you enjoy doing it, very simple integration. So d rho by rho is equal to minus k by v tank dt. So you can integrate it from say time equal to t1 to time equal to t2, say the density changes from rho equal to rho 1 to rho equal to rho 2. So you can find out how the density changes with time. Okay. So, important is not the solution of the problem, of course the solution is quite easy, but solution is definitely having some importance, but to my understanding the greater importance is what are the assumptions that are leading to the solution, because in reality the problems are not so simple as many of these ones. So, these might not be very common as our analysis equations, because if you see these equations that we have written, these are really on the basis of such simplified conditions or assumptions which might not prevail in practice. So, the final answer may be like interesting in terms of solving a particular problem, but the reliability of the answer may not be so strong, because you might have a strong variation of density within the tank itself, but at least by having a simplified assumption it is giving us a fair idea of like how the analysis should involve the conservation of mass. So, when we have been discussing about the conservation of mass, we have discussed certain types of problems. What types of problems we have discussed? We have discussed about one case when it is totally steady, that is you have like the density, first of all the density is not changing with time, volume of the control volume is also not changing with time, so that this term is not there. So, it is just a balance between the rate of outflow and inflow, and physically that represents a condition where rate of outflow is equal to rate of inflow. For that we have to keep two things in mind. One is that what is the sense of the velocity, velocity component normal to the area, is it going, is it opposite to the area vector or is it along the area vector. The second point is the velocity uniform over the cross section or is it non-uniform, accordingly we might need to integrate or not. And when it comes to a unsteady case, there are two types of possibilities. One is the density is changing with time, another is the volume of the control volume is changing with time, and maybe a third case when both are changing with time, but like we have perhaps not considered that case, but that is like it is a combination of the cases that we have considered. So, all these cases have given us a firm footing or understanding of how to use the integral forms of conservation equations. What is the advantage of use of the integral form of conservation equation? See, when you are using an integral form, the important advantage is that you are being abstracted from how things vary within the control volume. You are only bothered about a gross manifestation in terms of what is entering, what is leaving. So, what is happening inside, you are just representing it in an integral sense or an overall sense. You are not really representing it a point by point variation. So, we have to keep in mind here a very important thing. What is the difference between an integral equation and a differential equation physically? Differential equation gives you the variation at a point, whereas integral equation gives you the variation over a domain. Of course, the domain is constituted of many such points, but the differential equation is valid only at an identified point in the domain. So, the integral form, when you are writing, you may get back the differential form from that, but at the same time you are not forced to track or to keep in mind that what is happening as a point by point variation. So, that differential nature of variation you may not be interested in. So, in such cases where you are not really interested in that, it may be convenient to use the integral form. So, one has to keep in mind that when should we use the integral form and when should we use the differential form. It depends on the physical sense of the problem that we are trying to solve.